the holographic universe.
Okay, I'm intrigued.
So we've got a bunch of excerpts and notes here, all about some pretty heavy physics. Planck scale, the whole holographic principle, even some black hole theories. But
Jason dense.
yeah, but don't worry, we'll break it all down, make it something everyone can understand.
I think what's really fascinating about this is how these ideas, they started as kind of speculation, but now physicists are actually trying to find proof,
Yeah,
like in the real world.
that's what I find so cool, right? So let's start with something I always found mind-blowing, the Planck scale. Like, imagine shrinking yourself down, smaller, way past atoms, even smaller than a proton, and you keep going.
Okay, I'm shrinking.
You eventually hit this point where the laws of physics, like the ones we know, they just don't work anymore.
Really?
That's the Planck scale.
It's like the universe has a basement level and things get weird down there.
Exactly. It's where quantum mechanics and gravity, they start to intertwine. You have to rethink space and time.
I'm trying to wrap my head around that.
I know. It's hard. To give you an idea of how small we're talking, if an atom were the size of the entire observable universe,
Whoa.
the Planck length would be smaller than a tree.
That's ridiculously small.
It's crazy. So how does this connect to the holographic universe idea?
Well, the Planck scale, that's where this whole holographic principle starts to make sense. It basically says that all the information in a volume of space, like picture a box full of stuff,
Got it.
all that information can actually be encoded on the surface of that box. Like, those hologram stickers, the
Yeah.
flat ones that make a 3D image?
Yeah.
Kind of like that?
So wait, are you saying that what we see as 3D might just be an illusion, like a projection from a 2D surface?
It's a radical idea, I know.
That changes everything.
It has some pretty profound implications for how we understand reality, that's for sure.
Okay, so where do black holes fit into all of this? I know they're these super dense things, crazy gravity, but how are they connected to the holographic principle?
Right. Black holes, they have so much gravity, not even light can escape. And that boundary, we call it the event horizon, that's where things get interesting. Like, what happens to all the information that falls into a black hole?
Didn't Stephen Hawking, he worked on that problem?
He did. It was a big puzzle for physicists. If information just disappears in a black hole, poof, gone. That breaks some pretty fundamental laws in quantum mechanics. The holographic principle offers a solution, though. Maybe the information isn't lost, it's just encoded on the surface of that event horizon.
So instead of being trapped inside, it's spread out over the surface, kind of like data on a hard drive?
Yeah, that's a good analogy.
Wow, the event horizon, the ultimate cosmic hard drive.
Now, here's where it gets even more mind-blowing. If this holographic principle works for black holes, some physicists think it might work for the whole universe.
Wait, hold on. You mean everything we see, the entire universe, could be a projection from some 2D surface, like at the edge of the cosmos?
That's the idea. It challenges everything we think we know about reality.
This is all so incredible, but is there any way to test it? Could we ever know for sure if we're living in a giant cosmic hologram?
That's the tough part, right? Testing physics at the Planck scale, it's incredibly difficult with the technology we have now. But scientists are trying to find creative ways, like studying gravitational waves, those ripples in space-time.
Oh, yeah. I remember when they detected those for the first time. That was huge.
Yeah, and some think those waves might carry little hints about this holographic encoding.
Like glitches in the cosmic movie projector.
Exactly. We'd be looking for tiny deviations from what Einstein's theory of general relativity predicts.
That's amazing. So any other ways researchers are trying to test this?
Yeah, there's also the cosmic microwave background radiation, the CMB. It's like this afterglow from the Big Bang. And the patterns in it, they might hold clues too.
Those images are always so cool with those tiny temperature changes.
Right, and then there's high-energy particle physics, experiments like the Large Hadron Collider. Some models suggest that if the universe is holographic, there are limits to how much information can be stored in space, and that might show up in particle collisions.
It sounds like they're searching for anything unusual, any little thing that could point to a deeper reality.
Absolutely. It's like solving a cosmic puzzle, looking for the missing pieces.
This has been an incredible start to our deep dive.
Right.
We've gone from the Planck scale to black holes to the possibility that the universe might be a hologram.
And this is just the beginning.
Okay, so we're back, and our heads are still spinning a little from all that talk about the holographic universe. Last time we ended talking about black holes.
And how they might be these cosmic hard drives.
Exactly. But now I kind of want to dive into some specific theories, the ones that connect to the holographic principle. You mentioned string theory and loop quantum gravity.
Yeah, those are the big ones, right? When it comes to quantum gravity, those two are leading the pack. And both have some interesting ties to this holographic idea.
So string theory first. I remember bits and pieces from, like, forever ago. Something about tiny strings and extra dimensions.
Right. Okay, so the basic idea is that the smallest things in the universe, they're not particles, like little points, but they're tiny strings, one-dimensional strings that vibrate.
Okay, so not tiny billiard balls, but more like,
Like a cosmic symphony.
that's a great way to put it. So these strings vibrate, and that
That
creates...
creates everything, like the different vibrations. They determine what kind of particle is, an electron, a quark.
I see. So the universe is like musical at its core.
I like that. Now, here's the thing. To make the math work, you have to add extra dimensions. More than the three we experience, like up, down, left, right, forward, back.
Extra dimensions, that's always been a mind bender for me. How can we even picture that?
It's tough, for sure. Think of it like, imagine a tightrope walker. From far away, you just see them moving in one dimension, along the rope. But a tiny ant on that rope, it sees another dimension, the way around the rope.
Ah, so these extra dimensions could be curled up so small we don't notice them.
Exactly. And the cool thing is, within string theory, the holographic principle, it just kind of pops out naturally.
Now, that's what I'm curious about, the connection. How does a theory about tiny strings and hidden dimensions lead to the idea that our universe is like a hologram?
It all comes down to this thing called the ADAS-CFT correspondence. It's, well, a duality they found within string theory. Basically, it says that a theory about gravity in a higher dimensional space, it can be described by a simpler theory on its boundary, a lower dimensional one. And that simpler theory, it doesn't even have gravity.
So again, we're back to this idea of a higher dimensional reality projecting onto a lower dimensional surface, like that 3D image from a hologram.
Yep, it all connects. And the ADAS-CFT correspondence, it actually gives us a way to understand the holographic principle mathematically.
Yeah.
At least in some cases.
That's incredible. Okay, so what about loop quantum gravity? What's that one all about, and how does it connect to this holographic idea?
Okay, so loop quantum gravity, it's a different approach. Instead of adding extra dimensions, it tries to quantize space-time itself.
Quantize, you mean like break it down into tiny pieces?
Exactly. Think of it like, instead of space-time being smooth, it's more like it's made of tiny building blocks.
Like a cosmic Lego set.
Perfect analogy. Now, in loop quantum gravity, the holographic principle comes from how these tiny chunks of space-time interact. Turns out, the amount of information in a region of space, it's measured by its entropy. And that's proportional to the area of its boundary, not its volume.
Wait, so the amount of information you can fit depends on the surface area, not how much space is inside. That's weird.
It is strange, right?
Yeah.
But it fits perfectly with the holographic principle. Think of a book. The information is in the words on the pages, not how thick the book is.
I get it. So it's like the universe cares more about the outside of things than the inside.
You got it. And here's the crazy part. String theory and loop quantum gravity, they both seem to point towards this holographic principle.
So we have these two big theories about gravity, and both of them suggest that information might be more fundamental than we thought. And our 3D reality, well, maybe it's just a projection. My head is officially spinning.
I know, right? It's mind-blowing stuff, but we're still looking for proof. That's the next step.
Okay, so we've spent the last two parts of this deep dive really going deep, into the holographic universe. From the Planck scale to string theory and even black holes.
It's been a wild ride.
It has. But now I'm really curious about how scientists are trying to test these ideas. They're so abstract and complex.
Yeah, that's the key, right? We can have these beautiful theories and equations, but in the end...
The universe has to agree.
Exactly. So what kind of experiments are they doing to see if this holographic principle actually holds up?
Well, we talked about it before, but one of the most promising things is studying gravitational waves. Those ripples in space-time?
Right. Those were predicted by Einstein way back when, and we only just detected them recently in 2015.
That was a huge deal. I remember thinking, what else will these waves tell us?
And some physicists think those waves could actually hold clues about, whether our reality is holographic.
Really? That's fascinating, but I'm not sure I get how those two things connect. How could studying those waves tell us anything about the holographic principle?
Okay, so remember, the holographic principle says that all the information about a space, it's encoded on its boundary.
Yeah, like a 3D image coming from a 2D hologram.
Right. Now, those gravitational waves, they travel through space-time, and if the universe is holographic, they might carry little distortions, tiny imperfections, because of that encoding.
So it's like looking for scratches on a holographic film, and those scratches would tell us something about how it's all put together.
Exactly. Those imperfections, they'd be like deviations from what Einstein predicted. Really tiny, hard to find.
But if we found them, that would be huge.
It would be a big deal. Yeah, it would mean something really strange is going on with spacetime.
It sounds incredibly difficult. Are there any other ways they're trying to, look for evidence?
Definitely. Another thing they're studying is the cosmic microwave background radiation, the CMB. That's like the afterglow from the Big Bang, a snapshot of the really early universe.
Those images are always so cool, those little temperature fluctuations.
Yeah, and in those fluctuations, some physicists think we might find hints of a holographic universe. The patterns, how those temperatures are distributed, it could tell us something about how information was encoded back then in the early universe.
It's like cosmic archaeology, looking for clues in the oldest light in the universe.
I love that analogy.
Yeah.
And then there's also high-energy particle physics, experiments like the Large Hadron Collider.
The LHC, where they smash those protons together.
Yeah, and they think that if the universe is holographic, there might be limits on how much information can be stored in space. And those limits, they might show up in how particles behave when you smash them together.
So if we see something unexpected, something that doesn't fit our models, it could be a sign that we're hitting those limits, that there's this holographic structure underneath it all.
Exactly, like trying to put too much data on a hard drive. At some point, you run out of space and things go wrong.
It's amazing how creative physicists are, trying to test these ideas.
It really is. It shows how far we've come in our understanding of the universe and how much more there is to discover.
Well, this has been an incredible deep dive, exploring the holographic universe from those tiny Planck scales to the entire cosmos.
We've looked at these mind-blowing theories and all the ways scientists are trying to actually test them.
And even though we still don't know for sure what the true nature of reality is,
It's been quite a journey.
it has. And I think it's safe to say that the holographic principle, it's really changed how we think about the universe.
It definitely has.
Yeah.
It's opened up so many new questions, and it's pushing us to explore further.
So to everyone listening, keep asking those questions, keep exploring these ideas. The universe is full of mysteries, and the search for answers, that's what makes it all so exciting.
Absolutely. Who knows what we'll discover next?
Exactly, and that's what makes it all so worthwhile. So keep looking up at the stars, keep wondering, and we'll see you on the next deep dive.